All right, so yesterday we finished example 4, and what we were trying to do is we're trying to put together a bunch of pieces of information about a polynomial so we can talk about it without even trying to sketch it. And we said that the leading coefficient sign gives us the right end behavior, and then if it's an even degree, it's the same end behavior. If it's the odd degree, it's the opposite end behavior, just like we warmed up. Okay, but we also noted from this little activity up here on example 3, the relation between the degree and the number of x-intercepts and the number of relative extrema. Remember, relative extrema is just plural for relative max, relative min, or local max, local min. So we were working with the fourth degree polynomial. The parent function had how many x-intercepts? X to the fourth?
4.
Yeah, it has at most 4, but the parent function itself only had 1 x-intercept, and it had only 1 local extrema, a local min. But then if we look at transformations of it, now we have an example where we still have just the 1 local min, but we had 2 x-intercepts. So we could have 1 x-intercept, we can have 2 x-intercepts. This one over here had only 1 local min, or local max, sorry, but how many x-intercepts? 0. So in terms of x-intercepts, we already have seen 0, 1, or 2, but we've only seen 1 local extrema. So then we went to this one here, and we saw that it had how many x-intercepts? 1, 2, 3. So we've seen an example where we had 0, 1, 2, or 3 x-intercepts, but this one now has 3 local extrema, 2 mins and 1 max. So we jumped from 1 local extrema to 3, and then finally this one over here had how many x-intercepts? It had 4 x-intercepts, and that's at most. But it still had 1, 2, 3 local extrema. Okay, so just kind of summarizing, a fourth degree polynomial can have what combination of x-intercepts? A fourth degree polynomial. It can have 0, 1, 2, 3, or 4. So any number down to 0, but no more than 4. But in terms of the relative extrema, the only ones that we drew had just either 1 or 3. And we saw yesterday that if we try to add just 1 more relative extrema, the end behaviors would not work out. So we decided that turning points, local extrema, must occur in what? Pairs. In pairs. So the most number of local max or mins that a fourth degree polynomial can have is 3. But then fewer than 3, can we have just 2? No, we can only have 1. So I think you summarized a fourth degree polynomial has to have an odd number of local max or mins, with the degree minus 1 being the maximum. Yes, and that's what this theorem tells us right here. So that's why I reviewed all that. Here's a theorem. A theorem is a mathematical law, and it says if you have a polynomial of degree n, it has at most n zeros, and that's kind of alluding to the fundamental theorem of algebra. They could be, later on you'll see, either real or imaginary, but that's when the search is over. Fourth degree polynomial can have only 4 zeros or x-intercepts. Now we can have any combination down to 0 for an even degree function, but the relative extrema, the local max or mins, can have at most n minus 1. So a degree 4 can have at most 3, a degree 5 can have at most 4. And then these you might want to add, these must occur in pairs. They must occur in pairs. Because if you turn once vertically, you got to turn again to make sure the end behavior works out. All right, so the theorem gives you the upper bounds on both possibilities. Any polynomial can have fewer than the maximum, and we have to figure out what those other possibilities are. All right, so let's jump down to example 5. It says, draw several possibilities for the shape of a polynomial of odd degree. Use a fifth degree polynomial for an example. Okay, so we're just going to kind of sketch things. And I just need to make sure that when I'm sketching my graph, how am I going to make sure it's a polynomial? How do we spot a polynomial from its graph? Smooth and connected. It's smoothly connected everywhere in the domain is all real numbers. All right, so a fifth degree polynomial. Let's go ahead and see if we could draw it with 1 root or 1, 0. Well, I think I can handle that, right? Because the parent function itself for y equals x to the 5th, let's look at y equals x to the 5th. Remember, it looked a lot like x cubed. except it was flatter between -1 and 1. So there is an example of a fifth degree polynomial, and it has 1, 0. How many relative extrema does it have? Relative extrema, remember, means local extrema, which is max or mins. 0. Yeah, I'm going to call that RE for abbreviation, relative extrema. So 1, 0, but no turning points, no relative extrema. All right. Do you think we could draw it with 0 roots? Can you draw a fifth degree polynomial with 0 roots? Why not, Caden? Ah, very good, very good. When we were analyzing the fourth degree polynomial, it was entirely possible for the graph, because the end behaviors were the same, to come in the top, dance around locally, and then head back out the top without ever crossing or touching the x-axis. Same thing it could have done from below. Come in the bottom, dance around without ever touching the x-axis, head back down out the bottom. But for an odd degree polynomial, that is not the case, is it? Because they have opposite end behaviors and they're smoothly connected everywhere, there's no way to get from negative infinity to positive infinity without passing through what? 0. Yeah. So odd degreed polynomials must have, we'll say, at least one x-intercept. Guaranteed. Where even degree polynomials have no guarantee of an x-intercept. They certainly can. So for the even degree, like we saw with the 4, you can have either 4, 3, 2, 1, or 0 x-intercepts. But for this fifth degree polynomial, we're only going to be able to draw it with 5, 4, 3, 2, or 1, but not 0. Okay, let's go to the next extreme case. Let's see if we could draw the fifth degree polynomial with all 5 x-intercepts. Okay, and then we'll have the two extremes, the one with just the 1, the fewest number, and the one with the greatest number. So let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that would be a fifth degree polynomial, and it has 5 x-intercepts. 5 x-intercepts. And how many relative extrema does it have? 1, 2, 3, 4. 4 relative extremas. Okay, this one has 2 local max and 2 local mins, relative max, relative mins. So that would be the extreme case. Now, can we draw that fifth degree polynomial with just 4 x-intercepts? Yeah. Yeah, you have the option here. Instead of crossing right here and then coming back up, you could actually have it come up like this. I'll just trace over it. Come up, and instead of crossing there, remember, it could do what? It could bounce. And of course, when it bounces, there's only 1 x-intercept, but it counts as how many? 2. A bounce is a double root, okay? Because it does take up those 2 right there. So you could draw it with 4. Could you draw it with just 3? Then you would just have 1, 2, 3, 4 x-intercepts. It does count as 2, but it's only 1 number. So it has 1 physical manifestation. We call it a double root because it has a multiplicity of 2. It's taking up 2 roots, but it is only 1. Okay? And of course, then that would be 4. You can do the same thing with 3. You can let this green piece over here that takes up the 4th and the 5th, you can have it bounce off the x-axis as well. You can move this thing up or down if you wanted. Another way to get just 1 x-intercept is you can have it come in like this. 1, 2, 3. You can have it do that. That would just be 1 x-intercept. So there's lots of different ways you could draw these. The higher the degree, the more curves you can have. So I'm not so interested right now in drawing it with the different number of x-intercepts because I think that's going to be a little bit easier. Let's see if we could draw it with fewer relative extrema. If the theorem says that 4 is the maximum, then could we draw a fifth degree polynomial with just 3 relative extrema? Can we just have 3 relative extrema? Well, let's see. If I come in the bottom, I'll turn around once, bless you, twice, and 3 times. But if I'm not allowed to turn around again vertically, is that going to be a fifth degree polynomial? No, why not? The end behaviors are the same, so that's going to be an even degree polynomial. And so that's why, again, the end behaviors, or the returning points, the relative max and mins, have to come in pairs. So we can have three. So according to the theorem then, an odd degree polynomial can have an even number of relative extrema up to n minus 1. So what would be the next possible number? Just 2 relative extrema. Okay, so now we're getting into some uncharted waters here. How can I draw a fifth degree polynomial with only 2 relative extrema? Well, let's see. I'm going to draw one that comes in from the top this time. If I draw one coming in from the top, then it has to exit the bottom, yeah? Okay, so there's one of my turning points. I'll let it bounce right there. And here's another turning point. I've used up all my turning points. If I just go straight down like that, is that going to be a fifth degree polynomial? No, that's going to look a whole lot like a what? It would have 2 local max and mins, or a local min and a local max. So that looks like a cubic. That's going to end up looking like a cubic. So how can you distinguish a cubic from a fifth degree polynomial with only 2 relative extrema? Good question. I will show you. There's going to be some accounting going in for the lack of local max and mins. So if you drew this graph like that and made it appear like you were going to be turning back up, in other words, having another local max or min, but instead continue back down. That's kind of like it got kicked in the shin, like there's a dent in the can, right? So you got this little wiggle happening right here. See that? A little wiggle. It's the curvature of the graph is changing. It's like curving upward like a cup, concave up like a cup, and then it curves down like a piece of a frown. That is how you can distinguish a fifth degree polynomial from a third degree polynomial. Okay? What's that? No. What I'm telling you is when you see a wiggle like this, that makes it not a cubic, because the cubic would just have to be straight up and down like we did right here. And you don't have a lot of experience with this, which is what we're doing over now. So that would be the cubic. That is degree 3. But notice the brown one that I drew has, instead of just going straight down and crossing right there, it's wiggling right here. Okay? So if you have a graph that has a wiggle in it, that wiggle is accounting for, it accounts for 2 relative extrema. Okay, and here's why. If you think about grabbing that and twisting it, okay, just let that point be anchored and grab this right here and twist it like that. This graph, instead of doing that, could have turned up and then could have turned down. So here's the possibility. It could have done this, and then it could have done that. It could have gone up and then down. So if you twist this brown thing like this, you're going to get a local min and a local max. So a wiggle counts as 2 local extrema. So let's see how many we would have then. We would have definitely the 1, and then the 2, plus the wiggle, which counts as 2 more, essentially, that would be 4. So they're all accounted for. All right, now here's what's interesting about a wiggle when it happens on the x-axis. Let's draw something very similar, and I'll use purple here. Let's say I have a function comes in like that, and now on the x-axis, you approach like you're going to turn back up, like you're going to bounce, but instead you go psych and you turn down. Now that one only has 3 x-intercepts, yeah? Do you think it's a cubic? No, because there's a wiggle. And you got a wiggle happening right here. So I know that this is counting as, let's go ahead and say it counts as 2 relative extrema. Again, you could do the same twisting thing. But when it happens on the x-axis, look what it could have done. It could have come down like that, could have come up like that, and could have gone down like that. So there you see the 2 local max or mins that it's taking up by not doing that. But how many x values or x-intercepts does that one x-intercept take up? 1, 2, 3. Yeah. So a wiggle counts as 2 relative extrema, but it counts as 3 x-intercepts when it happens on the x-axis. Oh, boy, okay. So now let's see if we can count the roots. We have a multiplicity of what root here? 1? This is a multiplicity of, well, this would also be 1, so that's my second one. And that one counts now as 3. So 1, 2, 3. That's 5 x-intercepts accounted for. Only 3 are manifesting, but 5 accounted for. It's a 5th degree polynomial. These are not actually imaginary roots. Imaginary roots would be like over here. You see how this wiggle happened off the x-axis? Whenever you have a wiggle happening off the x-axis, this is what accounts for your imaginary roots. Okay, and the reason is notice this one counts as 1, and this one counts as what? 2. So physically on the x-axis, we only have 1, 2, 3 of the roots accounted for. And how many are still out there, unaccounted for? 2 more, and guess where they occur? They occur right there. When you have a graph that wiggles off the x-axis, that's your imaginary roots. Now, a wiggle is kind of a weird name. It does wiggle, but guess what we call that? We call that point, and it has a real name. It has an inflection point. Okay, why inflection? What happens if you're speaking and your voice inflects? When you're inflecting, when you speak, you're emoting. You're changing the tone of your voice so that for emphasis, right? So we call it an inflection point because something changes there. And what is it that changes there? The curvature. Good. The curvature changes at an inflection point. Okay, you could think of as you're coming in from the left, this is, we say, concave up, like a cup. It's part of a smile. Okay, at that inflection value then to the right, it changes now to concave down, we say, like a frown. So concave up like a cup or part of a smile to concave down like a frown. That's an inflection point. And an inflection point on a graph counts as 2 local extrema and possibly 3 roots, unless it happens off the x-axis. Yes?
So the bound of that is used, okay, so it counts for 2 when you're determining the degree.
It's a double root, yeah.
Finding the x-axis or the x-intercepts by themselves, that only counts for 1.
Right, because you don't want to listen, if, let's say that was x equals -3. You wouldn't say the x-intercept, the root, the solution is x equals -3 or x equals -3, because it's the same number. But because the factor is squared, it's 2 separate factors, 2 separate roots. Okay? So, there you go. Let's go ahead and summarize. An odd degree function can have, and then we'll put a bullet point here, an odd degree n, let's say, n minus 1, n minus 2, ... all the way down to 1 x-intercepts. But can it have 0? No. So what does this mean? Let's say I have a 7th degree polynomial n. A 7th degree polynomial can have either 7 x-intercepts, 6 x-intercepts, 5 x-intercepts, 4, 3, 2, or 1, but not 0. There's a guarantee of an x-intercept. And then what about the local extrema? It can have an even, any even number of relative extrema up to n minus 1. So a 11th degree polynomial can have what combination of local extrema? Either 10, 8, 6, 4, 2, or 0. Yeah, or 0. It's for an odd degree. Yeah, an odd degree polynomial can have 1, 2, 3, 4, 5 up to n x-intercepts, guaranteed 1, but an even number of relative extrema down to 0. If you want to add down to 0, that's not bad. You can have 0 relative extrema. Sure. Look at the parent functions up here. Yeah, you're thinking of x-intercepts. That's why it's important. They're related, right? They're related, including 0. An odd degree polynomial can have 0 turning points. Just think of your parent function x cubed. By the way, x cubed does what on the x-axis? Does it cross, bounce, or inflect? Your parent function x cubed. Are you visualizing it? It inflects, right? Your parent function x cubed inflects on the x-axis. So it has one x-intercept, but it counts for how many? 3. Yeah, because what this graph could have done is it could have gone up, turned, and turned. If you take that like that and you just twist it, now you have 3 x-intercepts and 2 relative extrema. So when the graph wiggles on the x-axis, it's counting as 2 extrema and 3 x-intercepts. Yeah, good question. That one you twist, you'd have to twist it a couple times. It would look like this. It would look something like that. You twist it more. Now that is going to have a multiplicity of 1, 2, 3, 4, 5. I'm not going to hold you accountable to multiplicities 5 because it's very hard to tell without quantifying the difference between a degree 5 twist and a degree 3 twist. So what I'm going to expect you to do is to look at a graph and determine if it's a single root, a double root, or a triple root, just from the graph, okay? A single root is going to be a cross, a double root is going to be a what? A bounce, and now a triple root is going to be an inflection point or a wiggle, okay? So if you want to think about it as cross, bounce, wiggle, maybe it's a dance, I don't know, that's fine. All right, so now here it says draw several possibilities of the shape of an even degree polynomial, use a 4th degree. We've already kind of done that. So let's just draw some examples here. You could have a 4th degree polynomial. Let's say it comes in the top, goes out the bottom. That's not going to be the parent function, but that would be a 4th degree polynomial, yeah? How many x-intercepts does it have? 1, right? But how many relative extrema does it have? 3. Is that the maximum amount for a 4th degree? Yes. 3 relative extrema. Could I draw that same graph with 0 x-intercepts? Yeah. This one's easy to do with notability. Watch. There's 1 x-intercept. If I move it up, how many x-intercepts? None. If I move it down so it bounces right there, how many? 1, right? So I go from 0 to just the 1. If I move it down a smidgen more, now how many x-intercepts? 2. And if I move it down even a smidgen more, where the other one bounces, now how many x-intercepts? 3. And if I move it down even more, now how many x-intercepts? 4. So that's a nice little illustration of an even degree polynomial. 0, 1, 2, 3, and 4 x-intercepts. So they can have any combination. But can I draw a 4th degree polynomial with just 2 relative extrema? No, because if I turn twice, let's say I come to the top, turn once, turn twice, now I'm heading out the bottom. And that's not good because they have to have the same end behavior. Yes, it'd be odd. So the next odd number smaller than 3 is 1. Can I draw a 4th degree polynomial with only 1 relative extrema? And the answer is yes. The parent function itself, that looks like x squared, it has a quadruple root on 0, but I'm not going to hold you responsible for that visually. So here's what I would expect you to see. There's 1 turning point. There's 2 turning points. Oops. We're doing a 4th degree. Sorry, let me start over. It looks something like this. Okay, now looking at that right there, how many turning points did that? How many relative extrema? It just has 1, right? And only 2 x-intercepts. Is that a parabola? Is that a quadratic? Heck no, right? There's no way that's a quadratic. What's this graph doing? Right here. It's wiggling. There's an inflection point somewhere about right here, where the graph goes from concave down like a frown to the left to concave up like a cup. That little point right there is going to be responsible for how many relative extrema? It's going to be responsible for 2 relative extrema and up to 3 real roots. So if that's 2 relative extrema plus the 1 relative extrema down here, that's 3 relative extrema, which means if you add 1 now, you're going to get the degree of 4. Because remember, the maximum number of relative extrema is 1 less. So how many real solutions does this one have? X-intercepts? It has 1 and 2. What's the multiplicity of those? They're both 1s, so that's counting for 2 roots. If it's a 4th degree polynomial, we know that we're going to have up to 4. Guess where the other 2 come from? It comes from the wiggle off the x-axis. If you have a wiggle on the x-axis, it counts for 3 real solutions. But if you have a wiggle happening off the x-axis, it counts for 2 imaginary solutions. Kind of strange. Okay? Getting it all straight? A wiggle on the x-axis is a triple root. A wiggle off the x-axis is a double imaginary root. But it still counts for 2 relative extrema. Okay, very nice. So let's go ahead and summarize here. Kind of the same thing we did there. An odd degree. Oh, we started with an odd. Let's do even degree. That's what we're doing, sorry. An even degree polynomial, n, function, can have n, n minus 1, n minus 2, ... 2, 1, and 0 x-intercepts. And that's different than the odd degree, right? Because we can have no real solutions, no real roots. Whereas in an odd degree, it's guaranteed, okay? And what about the relative extrema? If it's an even degree, it can have an odd number of relative extrema, REs, up to what? Maximum. Always n minus 1 for both of them. Okay, so a 12th degree polynomial can have at max 11 relative extrema. Or 9, or 7, or 5, or 3, or 1. Stardo. Okay. So hopefully as you're going through this, you're seeing some of the things that they have in common, but you're also noticing how they differ by the type of number the degree is, whether it's even or odd. All right, so let's summarize now. Here's a nice summary of what you're going to be responsible for. You're going to have to make the connection between the graph and the equation. So let's say you have a polynomial f of x and it's in fully factored form. Fully factored form. Try to say that 2 times real fast. Fully factored form, fully factored form. That's, yeah, that's hard. Fully factored form. Fully factored form f of x. F in fully factored form. You can add that to the front. F in fully factored form. So you have an a in the front. That is the a from our standard transformation form. That's your vertical dilation factor, okay? But let's say you have it factored as x minus a to the first, x minus b to the 2th, and x minus c to the 3rd power, okay? If you have it in fully factored form with your linear factors here, remember that the exponents on your factors represent the multiplicity of the root, right? Because this is a double factor. It's really x minus b times x minus b. So even though it has one solution, the factor's there twice, so the root will be there twice. And x minus c cubed is x minus c times x minus c times x minus c. It's a triple factor, so it's going to be a triple root. And so if you were to sketch a graph, you have an x-intercept at a, b, and c. So I just threw them on here randomly, a, b, and c. Now if you're sketching the graph, as you come in, how are you going to treat the graph at each value? Well, if the multiplicity is 1, you're just going to do what? Shoot straight across. Now, as you approach the double root, what are you going to do? Boing, you're going to bounce. And now, finally, the triple root, you're going to come in and you're going to approach it like you're going to bounce, but instead of going up here, you're going to go down. Okay, so that's all I'm going to hold you accountable for. A multiplicity 4 root looks a lot like a multiplicity 2 root. A multiplicity 5 root looks a lot like an M3. But it's hard to figure those out without quantifying. So I'm just going to hold you accountable to a 1, 2, 3. They look very different. What would be a possible degree for this polynomial? It's got to be an even degree because the n behaviors are what? Same. Because it comes in the bottom and goes down at the bottom, what should be the sign of a? Positive or negative? Negative. You can always refer back to your old friend x squared, right? Positive x squared opens up, negative x squared opens down. So if you have like an even degree polynomial and it opens down essentially, you know the leading coefficient's negative, okay? But remember, the sign can be determined by the right end behavior. So if the right end behavior is going to negative infinity, then you know a is negative. And that works for even functions as well, even degree functions. All right, now it's an even degree polynomial. Can you figure out what the actual degree is? 6. If you were to expand all this out, you have an x times an x squared times an x cubed. And if you add up all the exponents, you get 1 plus 2 plus 3, which of course is 6. So here's what else is cool. The sum of the multiplicities gives you the degree of the polynomial. The sum of the multiplicities gives you the degree of the polynomial. Is it time to go? 3 minutes. Okay, thank you, Coleman. The direct consequence is a very, very, very important theorem called the factor theorem. And we've been using the factor theorem this year, haven't we? Here it is. Wow, there it went by. The factor theorem says, if x minus a is a factor of a polynomial, then x equals a is a root of the polynomial. But because it's if and only if we can start on the right side, if x equals a is a root of the polynomial, then x minus that number a is a factor of the polynomial. So if you know a factor, you know a root, and if you know a root, you know a factor. And if you know a factor, you know a root. And of course, that means you also then know a factor. Yeah, sweet. So we're going to start with example 7 tomorrow, and we're going to push, push, push. Technology hopefully will work, and we're going to get this thing knocked out tomorrow. We're going to finish this section tomorrow, okay? Polynomials. Review your notes. What do they have in common based upon the degree? And how do they differ based upon the degree, whether it's even or odd? And there's a wallet on the ground down there. So it looks like Nolan's picture. There you go. Okay. Be working on your story. If you need some creative ideas, come see me. But try to like proofread your story and try to have some kind of plot. You know, don't just ramble on and then at the end say, and then I woke up.